Welcome everybody to the DIE seminar. So today we have the speaker is Miriam Benini from the University of Parma. She will speak about infinite entropy for entire transcendental functions. And let me remind you that you can ask questions by writing them in the chat, and then I will ask the question to the speaker, or you can just ask the question with your voice by using the microphone, up to your choice. So I think it's time, Miriam, to start. Thank you for being here.
It's so nice to be here. It's so nice to see many people that I haven't seen in a while, like Matteo Ruggero, Stefano Luzzatto, Fabrizio, Josias, and all of you from the DIE community. And so today's talk is going to be about infinite entropy for transcendental entire functions. In order to keep as close as possible to the main interests of the groups of the DinAmicI. So before even starting to define what a transcendental entire function is, let me observe that this result is not very surprising because entire transcendental functions have infinite degree. Okay, so it's kind of natural to expect infinite entropy. On the other hand, so they have infinite degree, so it's natural to expect that the entropy is infinite. In fact, we prove something stronger than just infinite entropy. The tricky thing is that the natural target space for entire transcendental functions, I'm going to get into this in a minute, but let me just tell you in advance that the target space is the complex plane, which is non-compact, and even has unbounded diameter, infinite diameter with respect to the natural Euclidean metric, and that the function is not uniformly continuous on C. So the first issue with this topic is to find a good definition of entropy. What is a good definition for entropy in our setting? Since we want to prove that it's infinite, we will want it to be as small as possible. We would like kind of to give a result which basically implies that the entropy is infinite with respect to any reasonable definition of entropy that you could give, okay? Now, if I say something which is too elementary for you, I am definitely not an expert on entropy. I'm rather an expert on transcendental entire functions. So if I say something too obvious, please forgive me. Okay. So one of the main things is what is entropy on such a space, okay? Before going into the entropy business, let me give you some very brief information on what is, I will try to keep my video on so I can look at you in the eyes. So let me try to give you some information on what we know about complex dynamics. So complex dynamics studies the iteration of a holomorphic map F from a complex manifold to itself. And holomorphic means that it has a Taylor expansion, and it's a bit stronger than being real analytic, okay? Holomorphic functions than being real analytic. Holomorphic functions are particularly rigid objects. And we will see some of these rigidity properties during our talk. Now, for this talk, though this question was motivated by problems in several complex variables, okay? Maybe in the end, I will say a couple of words about it since there are some people who are interested in this. But for now, let us take M to be of complex dimension 1. Then you basically have few possibilities for M. M could be the Riemann sphere. Or could be the complex plane, which are the ones who are most interesting for us. Could be the punctured plane, or the torus, okay? Up to biolomorphism and excluding what are called the hyperbolic Riemann surfaces on which basically everything is a contraction. These are in cases which are interesting to study from the point of view of dynamics. And for today, we will leave aside the punctured plane and the torus, and we will only look at the Riemann sphere and at the complex plane. So on the Riemann sphere, the natural holomorphic functions which act on the Riemann sphere are rational maps. That is, quotients of two polynomials. If I say something that sounds weird, just let me know and I will go on and explain, okay? So the natural maps who act on the Riemann sphere are rational maps, which are simply quotients of two polynomials. And the natural maps which act on the complex plane are transcendental maps, entire transcendental maps. What does it mean to be entire transcendental? It means that your Taylor series converges on all of the complex plane. This is the definition of entire. And transcendental means that you have an essential singularity at infinity. If you don't remember what an essential singularity is, which you probably all remember, but just in case, I will go over it later. But it essentially means that in any neighborhood of infinity, your map takes any value except at most one, which is called exceptional value. So you really see there is no way to extend your map to the closure of C, okay? These transcendental maps, really act on a non-compact surface. Non-compact in several ways, okay? You cannot compactify this surface, preserving even just continuity of your map. Forget about holomorphicity. So there are two classes of maps, which is not clear where they belong, okay? Like polynomials. You can see them as acting on the complex plane. You all know what polynomials are, right? So polynomials, you can imagine them to act on the complex plane, and you can also imagine them to act on the Riemann sphere by saying that, of course, a polynomial fixes the point at infinity. A polynomial is a0 plus a1z plus blah, 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 till an z to the n. And clearly, if you put z equals infinity, this will give you infinity. Okay, so they belong to maps who act on the Riemann sphere, and to maps which act naturally on the complex plane. And depending on what is more convenient to you, you will use one point of view or the other point of view. The other tricky thing are meromorphic maps. So meromorphic maps are defined as quotients of two transcendental functions. Well, at least one of them should be quotients of, I'm going to write two transcendental functions, but really at least one of them should be transcendental. The other one could be a polynomial, okay? It's the quotients of two entire maps, at least one of which is transcendental. Now, these maps, what is the particular thing about these maps? These maps have what are called poles. So they have points which, after one iterate, map at infinity. But at infinity, there is no way that your function can be defined. So they have points whose orbits are not well defined forever. Okay? This is the overview of complex dynamics in one variable. The main characters that you can find when you study holomorphic dynamics in one variable. Now, what about entropy? So it is well known that if you have a rational map or a polynomial of degree d, the entropy is log d. But not all of you may know that the story of this result is quite interesting. So very reasonable, okay? It's a bit tricky to have this relation between degree and entropy is a bit trickier than one would expect. There are maps of degree 1 that have entropy which is non-zero. Like, for example, if you take smooth spherical maps, which have some properties which are, if you take transitive spherical maps, the entropy depends basically on the rotation number. I have a question for the audience that we may answer later, is whether there are some known examples in non-compact spaces of maps with infinite degree and non-infinite entropy. So I would be curious about this because I looked for it online and I didn't find it, but maybe we can discuss this in the end. So entropy versus degree are strongly related, but not in a completely clear way. So how did people prove that rational maps of degree D and polynomials of degree D have entropy which is log D? The degree of a rational map is the maximum of the degree of the two polynomials which form the quotient, okay? So for rational maps, let me change a little bit. So for rational maps, why is this? Okay. Okay, better. So for rational maps, what you need to prove is an upper bound and a lower bound. Now, the upper bound, it has been known, so the upper bound is due to measure the lower bound, the fact that the entropy is bigger or equal than log D, which is the topological degree, is due to Misurevich and Petritsky. And this is from 77, okay? And it actually works, you don't need holomorphicity. What you need is a smooth, which in this case means C1, map F from a compact space to itself, differential manifold. While the other bound, the fact that the entropy is less or equal than log D, has been proven independently in a completely different way by Lyubich in 1980 and by Gromov in 1978. But it was only published in 2005. Okay, so a long time afterwards. And Lyubich actually, this was Lyubich's master thesis, and he basically was a PhD student. It was actually a master student at a university in Ukraine, and there he found this problem and he solved this problem. And only later he knew that in fact the result had been already solved in this manuscript, which did not have diffusion and was not published until much later. And it's interesting because this is what led them to the development of all the theory. There is a lot of theory of distribution of pre-images and constructing a measure of maximal entropy for rational maps, which basically originated from this question of finding an upper bound for the entropy of these rational maps and polynomials of degree D, and hence, and then obtaining that the entropy is log D. Okay, so let me tell you, if you just to set the scene before going to the actual definition of entropy that we're going to use in terms of an epsilon separated sets. So the observations about C, which I kind of said in the small introduction that I gave, is that there are two natural metrics that you can put on D. You can put the spherical metric and the Euclidean metric. Okay, so the Euclidean metric is exactly what you expect to be on the plane, and the spherical metric is when you imagine, just as a manifold, okay? Now forget about the function which is acting on it. You imagine it to compactify it, put infinity there, and then basically this would be a disk of some radius epsilon centered at infinity. So if you look at it in the complex plane, a neighborhood of infinity would be the complement of a disk in the plane. These are the two, and you can write it explicitly, etc., etc. Now, with the spherical metric, this space is totally bounded. Now, this may mean more for you than it means for me, because there are lots of results which hold for totally bounded spaces. while totally bounded means that it has a bounded diameter. Okay, so essentially that you can compactify to something which is compact. While with the Euclidean metric, this is not even totally bounded, which makes, I will tell it in a second, but which basically makes the entropy trivially infinite for even linear maps if you are not careful about the definition that you use. Okay, and then this is about the space. Now about the function, as I said before, if you take f transcendental, for us, whenever I say transcendental, I mean entire, okay? I'm always given for granted that these are entire maps. So you take your f to be transcendental, it's not uniformly continuous on C, and there is no way you can extend it to infinity. Okay, this is our setup. Now, let's go to the definition of entropy. You all know, okay, that there are two basic definitions of entropy. The one in terms of coverings, which I think was the first definition, was given by Adler, Konheim, and McAndrew. And it uses open coverings. And then there is the definition. And basically, since you only use covering, you only need the topological space. And then there is the definition by Bowen and Dinaburg. I'm not sure what is the history here, in terms of n delta separated sets. I'm going to give you the definition in a minute, okay? And this really works for metric spaces. And then there is the fact that everyone knows that if X, D is compact, D is a metric. So if it is a compact metric space, then the two definitions coincide. So in fact, the entropy that you define using a metric, which in principle depends on the metric and is a property, a geometric property of the space because it depends on the metric that you put, in fact turns out to be a topological property. Now, if I'm not wrong, on compact spaces, metrics are equivalent. This is no longer true in non-compact spaces. So as soon as you go to non-compact space, one of the reasons why this is true is that this is independent of the metric when the space is compact. Okay, and then it has many nice properties. I know that many of you are experts, okay? This is just for non-experts. So it is, both definitions are invariant under topological conjugacies. And this is really important because we want to think of the entropy as being an essential property of the dynamical system. So we want it to be invariant under change of coordinates. And then again, independent of the metric for compact spaces. Now, what is this definition in terms of an epsilon separated sets? I'm going to give the definition because then I'm going to tell you which exact definition I will use for entropy. And it's based on a modification by Bowen of this concept of entropy on an epsilon separated sets. So definition. If we take XD to be a compact metric space, and F from X to itself continuous, a set E is called N delta separated, if for any 2 points, I'm going to draw a picture in a second for those of you who are not familiar. So if for any 2 points in the set, which are distinct, there exists some iterate smaller than n, so there exists some k, such that the distance between f to the k of z and f to the k of w is at least delta. Okay, it essentially an n delta separated set is a set of points which may start very close, but within a fixed number of iterate, n, end up being delta separate. Some of them may be separated to start with, some of them we may separate at the first step or at the second step, but they need to get separated before n, each single pair of points. Okay, and then you look at the cardinality of those sets. Okay, and you really see that this is, so look at the cardinality of these sets, K, you call K and delta. Sorry, there is some notifications that I get. C and delta to be the cardinality, maximum cardinality of n delta separated sets. And what is your topological entropy? It's the growth rate of this cardinality. Okay, so it's the sup over delta of the limb sup of the growth rate is always done by taking the logarithm and dividing by n. Okay, this sup is sometimes this sup is sometimes a limit, but of course, as delta goes to 0, you get more sets. It's easier to be separated when delta is smaller. So taking the sup or taking the limit is the same. Now, what is the problem of this definition from our point of view? If you have a space which has infinite diameter, you can clearly find sets with arbitrarily many points, which are separated to start with, okay? So with this definition, if your space has infinite diameter, if X is no longer compact, and it has infinite diameter, then your topological entropy gets infinite even when your map is linear, okay? So if I look from this point of view, if I look, do you remember our polynomials? And if you want our rational maps, but let's say polynomials to be mathematically precise, okay? If I look at our polynomials as mapped from the Riemann sphere to itself, we are all happy. We have a compact surface, but a compact space. But if we look at it on C, using the metric on C, under this metric, the space has infinite diameter, so the entropy gets infinite. So this is not the good definition because everybody has infinite entropy. And so transcendental maps also obviously have different entropies. So what was one of the many, there are many different definitions of entropies on non-compact spaces, assuming various degrees of properties of these spaces. And a good reference, I think, for non-experts for different kinds of entropies on non-compact spaces is a paper by Hasselblad, Nitecki, and Prop. Okay, and this is where I found this definition. And you basically take this definition, but instead of looking at every set that you can find in your space, which has infinite diameter, so you can take as many points as spaced apart as you want, you look only at compact sets. You look only at orbits which originate from a compact set. So what you do is, so one possible definition, we actually strengthen it a little bit, but let me give you the definition by Bowen. Bowen gave several definitions, okay? So the definition that Bowen gave is that you take your XD metric, no longer compact. Almost there, math is about to start. This is the last piece of the introduction, and then we're actually going to prove something. So you take a space metric, no longer compact, and you take a compact subset. And you only consider sets E contained in K, which are n delta separate, to define, again, your maximum cardinality restricted to K. So Ck n delta is the maximal cardinality of E n delta separated in K. And of course, you will define the topological entropy. Well, topological entropy restricted to K will be the soup Fk will be, again, the soup over delta, the limit for n which goes to infinity, 1 over n log of this C and K. And what will be the entropy of all your space will be the soup over compacts over the topological entropy on compacts. Okay. Now, questions? Very reasonable, okay? Observation 1. K is not required to be forward invariant. So what are you doing here? You're taking your K and looking at orbits which originate in K, but which may exit at the very next step. Okay, so when you consider your n delta separated sets, you really look at sets which starts in K and then emanate from it and are free to expand all over the place. In other, even more restrictive definition, you can ask for K to be forward invariant, but this is not the definition that Bowen gave. Okay. Second observation is that there are several other definitions in the paper by Hasselblatt, Nitecki, and Prop, and they prove a proposition in which this definition of entropy gives you the smallest of the entropies that I define. Of course, I'm not saying that out of the dozens of definitions for non-compact spaces, there are definitions which will give you smaller entropy than this. For example, you can assume K to be forward invariant, okay? I'm just saying that it is a relatively restrictive definition of entropy, which will not give you the highest possible level for the entropy. Now, when we wrote the paper, we were not happy about asking K not to be forward invariant. So what we did ask was a weak condition of invariance. Now, what we did ask was that a set E to be n delta separated would also need to have their iterates contained in K for at least Kn steps. Okay, so this is the definition that we used. Basically, look at orbits which emanate from compact sets. Define n delta separated sets as sets on which every couple of points get separated by delta before n steps. And we also ask that these sets stay in K for the number of times that it gets them to get separated. Now, what is one of the key facts that is kind of known? So what I'm saying now, what is this definition of entropy relates how points get separated, but it's a fact which is basically what Mizurevich and Przyczki proved, is that if you have many preimages, which means the degree is high, then the entropy also needs to be high. Okay, let me formalize this theorem because the proof by Mizurevich and Przyczki works on compact manifolds. So this is a general theorem. Is that this is formulated for holomorphic maps, okay? But the way we proved it for holomorphic maps, I'm sure in a different setting could be generalized. This is not something very deep, it's just an observation. If you take a bounded open subset of C, now we start doing some complex dynamics, okay? If you take a bounded open set of C, and you take your map to be holomorphic in a neighborhood of V, in a neighborhood of, well, of the closure, then if every point has at least n preimages, in V, then the topological entropy on this set is bigger or equal than log n. Okay, not surprising. We may go over the proof in the end of the talk, but this is something that will not surprise anybody. Okay, so what are the observations here? First of all, that, well, you can replace n preimages by counting them with multiplicity if you want. Which is a bit stronger, because n preimages means really that every point has n distinct points which map to it. Counted with multiplicity may mean that your point has all their preimages concentrated in one point. Of course, for holomorphic maps, this cannot happen in too many places, so it will not spoil your result. Okay, and so one observation is that the degree is not even well defined in this case. Okay, so this is why we talk about number of preimages rather than talking about degree. And the second observation, which is the key observation, is that we reduced computing the entropy by finding sets such that their image covers them at least n times. Okay, so basically we took our problem and we reduced it to a purely geometrical problem in terms of holomorphic maps. So what will be our goal? Will be, give me a transcendental function. I will give you a set whose image covers this set at least n times for every point. And then it will follow that the entropy is n on this compact set, and I will find it for arbitrarily large n, and this will give me infinite entropy. So what is the theorem that you actually prove when you look at holomorphic maps? And here we really use the fact that the function is transcendental. Okay, this proof does not work for polynomials and the rational maps. I think it definitely doesn't work. So theorem, was done with Furness and Peters in 2018. Maybe I will say a few words about the motivation in the end. So it's from 2018, it's relatively old, okay? I just thought it was the most appealing topic for this audience. Now the theorem will be that you take f transcendental entire function and you fix your n as you please. Then there exists a non-empty bounded open set V such that f of V covers V at least n times. This covers V at least n times is exactly what I told you before. It means every point in V has at least n preimages in V itself. Oh, this is not compact. Don't worry, take the closure, okay? It's more natural to look at covering properties of open sets, but in fact, what you really do is that this holds for any point in a closure. It feels more natural in this setting to formulate it for open sets. Now, it's really surprising how the idea this is a super elementary proof, okay? And it uses only basically three ingredients: Picard's theorem. I'm going to state it in a second. The fact that entire functions grow faster than any polynomials, transcendental functions grow faster than any polynomials. And a little bit of hyperbolic geometry. So for those who know the hyperbolic metric, you use a little bit of properties of the hyperbolic metric. For those who don't know, I'm going to tell you exactly what you need and what is true in this holomorphic setting. So Picard's theorem tells you that if f is transcendental, it takes every value except at most 1. In every neighborhood of infinity. The fact that it grows faster than any polynomial, it tells you that on any circle of sufficiently large radius R, you can find a point W in this circle such that the modulus of f of W is bigger than R to the K, okay? For each K, there exists some R such that on this circle CR, R as big as you want, so that the modulus of this point, so W is on the circle, so the modulus of W is equal to R, there exists one point, you may not choose which one, but you know that one exists, which is mapped very far away, farther than any polynomial, okay? In fact, you need a bit less. Now, so basically well, I'm gonna explain this in a minute, but let me tell you a little bit of what you need geometrically, okay? I'm saying it now so that it makes more sense when I do it in the proof. Of course, I'm only going to prove the simple case, okay? The more complicated case, I'm not gonna deal with it. So what is this theorem to say that you find these sets which cover themselves n times are particularly simple to find when f omits one value, okay? Picard's theorem, there may be one value which is emitted, but at most one. Suppose it's 0. Suppose there exists such a value, and suppose it's 0. Of course, that it's 0 or 25 or 2 million E, we don't care, okay? It's just up to conjugation. But so the simple case is that f omits 0. So this is the case that I'm going to deal with today. And maybe I'll tell you a couple of words about the other case, but it's just more complicated estimates and you have to be a bit more careful. So this is really the case which clarifies the geometric proof of this result. So I think these techniques are very different from the techniques that you usually use in other types of dynamical systems. So I think it can be kind of interesting to see how the special properties of holomorphic maps allow you to prove results which are true in much more general classes, okay, with completely different proofs. So what is that you need to know? You need to know that if you take an annulus of internal, you fix your R, you take an internal radius R over 2, external radius 2R, then somewhere in between you will have your circle of radius R, and this is one of the spaces that we are considering. The other space is C minus 2 points. Okay, this is our omega and this is our annulus. Then all you need to know about geometry is that there exists two metrics. One in this annulus, I call it rho A, and one is this set omega, I call it rho omega, such that the diameter of this circle is bounded independently of R, which basically tell you that this metric is invariant under rescalings, okay? So the diameter of this inner circle, when you change R, is like rescaling your annulus. This diameter does not change. It's like saying your metric is invariant under rescaling. Of course, for those who know, this is the hyperbolic metric, okay? But it's not important that you know the definition of the hyperbolic metric. The important thing is that this diameter is bounded independently of R, and that thanks to the special properties of holomorphic functions with respect to this metric, the diameter of f of CR is also bounded. This one in, sorry, this is the diameter in A, because CR is in A, and its image, where is it? Its image is in this set rho. You can do this because you omit 0, and forget about the second point for now, okay? So the diameter of this image, of the image of this curve in the set omega, is also bounded independently of R. And the last thing that you need to know is that the length of any curve in this omega, well, also in annulus, but we don't care in the annulus, okay? But the length of any curve which goes to infinity, is infinite. So if gamma is any curve connecting a point to infinity, then its length is infinite. Okay, what does it tell you? It tells you that the image of this CR under your F, if it omits 2 points, one we know it omits it's 0, okay? We chose the function that omits 0. If it also omits another point, this will be some curve in this set. Gamma should not have been. So your curve gamma, well, you know what gamma is. So the image of this curve CR may be something complicated, but since it has bounded diameter, and since the distance of any point to infinity is infinite, it cannot go too far. Okay, this is all that you need to know in order to understand how you will find these sets. Okay, it may look a bit mysterious at this point, but let's see. Another observation: how do you get n distinct preimages? Think of a map. Okay, think of a map that you know. You take a point, you apply this map, and it will give you n distinct preimages. Yes, it's that n. Okay, so observation. The root, the nth root of a point, the set of nth roots of a point z in C are exactly n points, and they're even nicely separated. Okay, this is very similar. Many of you may know the proof of how you show that z to the d restricted to the unit circle as entropy log d. Okay, what you basically do is you take roots of higher and higher degree, and they're nicely equidistributed, and you take a point, and this will have roots, and you can study this. Okay, so in a certain way, it's kind of similar. So if you take a point z, which is on some circle of radius r, you will get exactly n points on the circle of radius square root of r when you apply the root. Of course, the root is not a function, okay? It's the inverse of a function. It's a branch covering. Well, you need to think a little bit about it. Now, how do you prove the theorem? So what was the claim? The claim was that you fix n and you find a set V such that, well, V will be an annulus. So let's draw an annulus, okay? Actually, it will be exactly our annulus that we draw with appropriate radius. So you want to find a set V such that its image may be horrible, okay? It will be an annulus. But what you really know, and then you will have some internal curve, but what you really know is that the image contains your original annulus. So you need the image to cover all of your original annulus, and moreover, you want any point in this annulus to have at least n preimages in the annulus itself. So how do you do this? Now, you remember we have only 3 ingredients: Picard's theorem, growth, stronger than any polynomial, and a bit of geometry. So let's use the first 2 ingredients. So we fix, how do you choose R? Basically, all the point is in choosing this R so that you will have this nice covering picture, okay? So how to choose R given n? You choose a circle of radius R such that you have one point, Wm, whose image is small. In fact, you could do it much more precise. You could say is as close to 0 as you want, but you don't care. This is more than enough, okay? And you can do this for arbitrarily large radii because Picard's theorem tells you that points with modulus less than 1 have preimages on circles of arbitrarily large radius, okay? You cannot choose your radius precisely, but you know you have infinitely many of them for which this happens. Now, if your radius is big enough, you can also find another point, which comes from the fact that your function grows a lot. And for this point, your image is very big. How big? You need it bigger than r to the 2n. Remember, n is fixed. Well, I use the small n here, okay? I hope it's not too confusing. Almost done. So, and what do? You define a function g to be essentially a root, an nth root of your function f. So you can find, this you can do because your function omits 0, okay? If it doesn't omit 0, it's more complicated. This is one of the technical issues. You can find, because f omits 0, you can find g such that g to the n is equal to f. Okay, you can find g is an nth root of f. So for example, if f is e to the z, g is e to the z over n. Or you can also choose any other branch of the root. Okay, this is just an example, just to understand what we mean by taking the root of a function. Careful, because this n here is an exponent. It's not an iteration, okay? Basically, there is not a lot of iteration here. Now, the second thing that you do, so this you can do because f omits 0. The second thing that you can do, that you want to do, is to show that the image of the annulus AR contains the root of the annulus itself. Why is that? I'm going to draw a picture and this will be clear, okay? Now, why do you want to do this? Because look at the picture. We have our annulus AR. It's here, okay? And f is doing something to it. We don't know. But we prove, I haven't proven it yet, this is where geometry comes in. We prove that when you apply g, the image of g under this annulus is some big set, okay, which covers another annulus. And of course, these are all in C in the same plane, okay? But I imagine them to be in distinct planes so that the picture makes more sense. What is AR 1 over n? Well, if AR is by definition the set of points whose modulus is between r over 2 and 2r over and 2r, then the nth root is points which are between r to the 1 over n over 2 to the n and 2 to the n r to the n. Okay, now let's look at this picture because this is the key of the whole proof. You have your g is sending your annulus AR to some set which covers the root of this annulus. But who was f? F is just the polynomial which sends z to the n. F is equal to g to the n, okay? So it's basically g composed with the polynomial which sends z to the n. So once I go here with g, to find f, I just have to compose with this polynomial Pn. The polynomial z goes to z to the n. And this annulus gets mapped exactly to this annulus under this polynomial. So when I compose and then look at what f does, what happens here? Well, since g was covering this annulus a r over 1 over n, the image under f of this AR will cover the annulus AR. So what are we missing? The nth preimages, right? If we don't just want questions.
Yeah, there is just an observation in the definition of AR to 1 over n. I guess also there is a 2 to 1 over n is a net, right?
Sorry. Thank you. Okay.
So this is a to the AR to the 1 over n.
Yes, yes. Yes, I think you should have refreshed. And one, sorry.
Okay, thanks.
Thank you. So when you apply z to the n, this nth root of your annulus gets exactly mapped to your annulus. Okay. where do the n roots come from? Now, look at this. Here you have a point. Now, colors are a bit tricky, so I'm going to erase a bit of colors, okay? Otherwise, we don't see the points. Not the arrow. So G was going there, and F. So take a point here. Who is F minus 1? F minus 1 is G minus 1 composed P minus N minus 1. Pn minus 1 does not make a lot of sense because you cannot invert Z to the N. But what we mean by this is for any branch of the nth root, each one of them can be considered as a branch of the inverse of Pn, okay? So when I take a point Z here, how do I find its preimages under F? Well, first of all, I do the preimages under Pn. These are exactly n points, which are even nicely distributed. We don't really need this, okay? But they are nicely distributed. The separation will come from the fact that you have some compactness argument. You don't even need to know that the roots are nicely distributed. And then I take preimages under G. Each of these points in the nth root of the annulus has exactly one preimage under G, which will end up being exactly preimages of this point Z. Maybe we should change color for Z. And each one of them will be mapped to Z under F. This is the way you get n preimages. We still miss to show that the image of G, the image of AR under G actually covers AR to the 1 over n. Okay, how do you do this? Just in a few words. How do you do this? You simply say, suppose it doesn't. Okay, if it doesn't, then the image under G omits 2 points, 0, which we know from the beginning, and some other point. So let me do a fresh picture, otherwise this will not be clear. So if the image of this AR under G does not cover all of AR to the n plus 1, AR 1 over n, then it means that you don't omit not only 0, but also some point here. But then what happens? That the diameter of your image is bounded, so it has to stay on a compact set, but you have one point which maps very close to 0 because it has modulus less than 1. You remember the choice of W small m and W big N, and one point which maps far away. Contradiction. Okay? Contradiction comes from your metric, which tells you that the diameter of the image of this annulus is bounded in your set, which is C minus 2 points, 0, which is always omitted, and the other point that you assume by contradiction is going to be omitted. On the other hand, the way you choose your R, is that the diameter is very large, because it has one point close to 0 and one point far away, and the length connecting them is infinite, is very long, it's arbitrarily long. Okay, so the distance between these 2 points, the diameter has to be arbitrarily large. Now, so what happens when F does not omit 0? Your set V is no longer an annulus. You need to take care of many more. Your set V, you can no longer choose it to be an annulus. You can no longer choose it to be an annulus means you can write a function for which it's impossible to find annuli who cover themselves. Okay, it's not just we didn't make the proof work. You cannot choose it to be an annulus, and you need to look at other candidates and divide into cases and actually do estimates. If you notice, there were no estimates. It was all a soft argument. You have a set which is bounded and its image is bounded. When you go to functions which do not omit 0, the things become more complicated and you unfortunately have to look at precise estimates. Now, what else do I want to say? Well, just as a curiosity, this problem came up because we wanted to look at entropy for some automorphism of C2. So maps from C2 to C2 who are of degree 1, which are holomorphics, okay? Which are, how do you say it, in non-holomorphic way? Well, we originally wanted to study the entropy of some specific maps which are not polynomials. In C2, you can also have polynomials, which are kind of defined in the way that you imagine. You can have non-polynomials. Not sure whether transcendental is a good term in that case, but we wanted to study the entropy of some non-polynomial maps from C2 to C2. And when we went to look for a way to prove that the entropy was infinite, we realized nobody ever proved that the entropy was infinite, even for maps of C. Of course, when you find a result that is supposed to be kind of obvious and nobody has a proof, what do? You start asking all your colleagues whether they know if there is a proof, right? What would you do? You ask your colleagues who know better than you. And nobody seemed to know of any proof, so we did prove it in the way that I just showed to you. Obviously, after you put your preprint on archive, somebody writes you 3 days after telling you that in 2005, somebody wrote the statement of this theorem in his thesis in German. And so it turned out that in fact there existed a proof, which was a manuscript. It was never published. Now it's published because we insisted that he put the now we insisted that he at least put the manuscript on archive. So there was this student in Germany who used completely different methods, very beautiful proof, though much less elementary than ours. Our proof uses nothing, okay? Our proof is like super elementary. His proof is super elegant, super beautiful, but uses some very strong theorems. So it turns out this result was not really new, but we only discovered it after we spent some time proving it. And well, that's it. Questions? We did prove the result also for the maps of C2, but that's another story.
Okay, so thanks for the moment. So let me ask if there are questions or comments. Please just. So maybe I can ask just a quick question that maybe was hidden in your other proof that you didn't show. So for a specific f, if you have a given f, so is it interesting to have a more quantitative proof of this theorem? Let's say I have estimates on V and the annulus and that you have to choose.
Neither proof gives you precise estimates on how far you have to go with R. So your R depends, where you have to go depends on having a point which maps back and then having a point which maps far to infinity. Okay, you need one point which maps close to 0, modulus less than 1 point which maps far away. So estimates on where to find points which map far away are super easy to find. It depends on something called order of growth of the function. But in general, so if you have a function which has, for example, an asymptotic value, you can basically use these estimates for mapping far away, and you know for free that you will have points mapping back. So in fact, in some cases, when you have asymptotic values, you can find precise estimates on where to find this disk. Like for the exponential, you can estimate it precisely.
So that you have to know how far you have to go to obtain.
Yes, for the I cannot do it on the spot, but I know how to do it. For the exponential, for any map who has an asymptotic value, and for which I know the order of growth.
But when you mention quantitative estimates in the case that f does not omit 0, was it related to this, or what kind of quantitative estimates you need?
You need to understand exactly how. So you remember we had this annulus and the central circle in between, and the central circle has a certain diameter in there. Yeah. According to this metric, this which are the hyperbolic metric. You map it forward, and you need to find the precise estimate for the diameter of the image set. It's not enough to say that it's bounded, and then you need to make several other estimates. The proof moved from half a page, which is the one I told you today, to 15 pages with the same idea.
Okay. Are there other questions, comments?
I have another question, which I'm afraid might be really very silly. So in case, just forgive me, Miriam. Going back to this definition of entropy that was given by Bowen, and then you made a remark that you want to have a different one. You want to add this condition on these sets E whose points are n delta separated. why do you want that, and what difference does it make in the end? I mean, what consequences does it have to use a different definition?
So there was just no, so it's slightly more restrictive. So it's slightly more difficult to get infinite entropy if you also ask that your iterates stay in your compact set for n steps.
How often do they differ? I mean, do you have examples in which the two things?
No, I don't know. Okay. I don't know if they're different. I think if you, actually, it's a good question. I asked myself this question and I didn't find an answer. So in fact, you could ask for your compact set to be forward invariant. This is another possibility to define entropy in this setting. Well, you are the expert on, well, anyway, I'm not the expert on entropy, okay? I studied it in order to write a decent paper, but so the thing is the following. You can ask K to be forward invariant, and this would clearly give you a more restrictive condition. I think in our setting, it should be possible to find a forward invariant set by taking limits of backward orbits. But I'm not 100% sure. In situ, we actually find forward invariant sets, which are n delta separate. We find completely invariant sets, which are n delta separated. So we can use an even more restrictive definition of entropy. But I don't know if in our case, it may be that they are the same one. I'm not sure. In general, I don't think they are, but I don't have examples.
Your idea was you want a reasonable definition that stays away from being infinity as much as possible. Something
exactly. Like we wanted to kind of find and in a way, I think our covering result that you find compact sets which have, for arbitrary n, you find compact sets for which each point is n preimaging is kind of, this is not math, okay? This is hand-waving, but it should prove that the entropy is infinite according to basically any reasonable definition.
Thank you.
So does anyone know examples of maps with infinite topological degree and non-infinite entropy? It's tricky because you need a non-compact space, and I think you also need non-totally bounded. I don't know. You need Mizurevich and Brzezinski not to work. By the way, on compact spaces, I don't think you, well, I don't know. We don't know.
So let me ask if there are answers from the audience. No.
Well, let me ask you a question. So by infinite degree, so if you have a non-smooth map, like just an interval map with an infinite number of branches, yes, I think it's exactly what John is saying. If you have just like a interval map with an infinite number of branches, like the Gauss map, would that count as having infinite degree?
I think so. What is the entropy of this map?
Oh, I guess it's got infinite entropy. I don't know. I'm not sure. John probably knows.
Hi, Stefano, by the way. I haven't seen you in 2 years or something.
Yes, hi.
Yeah, the entropy of the Gauss map is infinite.
Yes, exactly. No, I was thinking of that example, but then I realized, it's not a counterexample. So yeah.
I don't know.
But it seems like it should really be something that should be possible to prove that you automatically have infinite entropy in that case.
Should be, but
it's an open question.
I'm not the expert on entropy. I didn't find the theorem which tells you that. Because most theorems on entropy are on compact spaces, as you all know. I mean, there is so much to do on compact spaces that people don't look too much on non-compact spaces. You know better than me.
In the meantime, there's an interesting conversation in the chat line, which is not going to be recorded.
I want to read that. What is going on in the chat?
You want to take a look?
So maybe we can continue this nice conversation after closing the YouTube.
Maybe.
So let's do this. So let's thank the speaker again. And
Guys, thank you for listening.